Right, so molar solubility is just another equilibrium with a solid and the ions that it produces in a solution. And when we're calculating that, it pretty much calculates exactly the same as all of our other equilibrium expressions, except that we're using S to represent that molar solubility rather than X like we use for other solutions. And the molar solubility tells us essentially how much of each thing will dissolve into a solution. So we can use that to calculate, oh yeah, well, that's impure water. Well, actually, no, this is a good example. So when we set this up, we set it up sort of as an equilibrium again, and this is plus S and plus 2S. And I want to highlight that because that 2S is going to disappear later. The reason it's a 2S here is because we're saying we're starting with some solid in the solution and how much of each ion is going to be made in the solution or present in the solution. And because for every iron hydroxide, I get 2 hydroxides out of it, this is plus 2S. But if I was to write out just the solubility expression, it would be KSP is equal to the concentration of iron times the concentration of hydroxide squared. So we'll see that become relevant soon. So we calculated KSP from molar solubilities, calculated KSP, and then we were just at the very, very end of the last class talking about sort of comparing the solubilities of different compounds. And when you have different numbers of ions that are being produced in a solution, you can't compare them directly. So magnesium hydroxide has a KSP of 2.06 times 10 to the negative 13. When it dissolves, I get 1 magnesium and 2 hydroxides. For iron carbonate, the solubility is 3.07 times 10 to the negative 11. And that's a larger KSP, so we might expect it to be a larger molar solubility, except it only produces 2 ions in solution, the iron and the carbonate ions. That changes the math. And so sometimes things that have close KSPs, we cannot use their molar solubilities to predict which one's going to be more or less soluble. On the second table, we've got 2 things that both produce 3 ions. So the magnesium hydroxide produces 3 ions. Its KSP again is 2.06 times 10 to the negative 13. And when we compare it to something like calcium fluoride, which also produces 3 ions, 1.46 times 10 to the negative 10, those molar solubilities then, well, because of the KSPs, or we can compare the KSPs and predict that the molar solubilities are going to be sort of in that same order. The larger KSP will have the larger molar solubility. The smaller KSP will have the smaller molar solubility, but only when there's the same number of ions. Kind of a little asterisk on molar solubilities. The new thing that we're talking about today, at least first, is the effect of a common ion on solubility. Because you remember Le Chatelier's principle from chapter 16? That was a while ago. If I have, or if I add something to the right side of this equilibrium, that's going to make this reaction shift to the left. And it's the same thing here because we're still talking about equilibrium. It's just equilibriums of solids with their aqueous ions. So if I have calcium fluoride and I put it into a solution where there's already fluoride ions present, that's going to suppress how much of it dissolves. Because for this to go to the right, I'm adding to fluoride, which already has ions there. In a way, it's kind of blocked. So that it will reduce the molar solubility. And so we have to calculate what the new molar solubility is going to be. So molar solubility of calcium fluoride is this KSP, 1.46 times 10 to the negative 10. And on all of these, should always just write out what it's going to dissolve into, because that equation is important for determining the rest of what's going on. So here, when we're calculating molar solubilities, we're still talking about what concentration of each ion will dissolve. So this is like an initial state where I don't have anything dissolved, and then I will dissolve something and get a new state at the end. So we're essentially doing an ice table. The initial concentrations of these will be, well, not both 0. Normally it would be 0, but we have already 0.25 molar calcium nitrate in the solution. And so that's going to mean that there's already, because calcium nitrate, nitrates are all soluble, there's going to be some concentration of calcium in the solution. There's not going to be a concentration of fluoride. And then these will change by some amount, and really molar solubility, we're calculating what is that amount of change going to be. So I'm adding, oh, not just S, this is plus 2S. All right, so like all the other equilibrium problems we've seen, and this will be 0.250 plus S, and then this is 2S. And so those are going to determine what my concentrations of calcium and fluoride will be at equilibrium. And now I can take those and I can plug those into KSP equals calcium 2 plus times the fluoride concentration squared. KSP is 1.46 times 10 to the negative 10 equals, actually, before I write this in, just like other equilibrium problems, we want to try and simplify them as much as possible. So can I assume that S is going to be a really small number? Yeah. With, other equilibrium that we looked at, we said like at least 10 to the minus 3. This is 10 to the minus 10, which is not just 3 times bigger, it's 10 million times, or sorry, not 3 times smaller, it's 10 million times smaller. So this is definitely going to be a very, very small S. And so we can assume that this S is going to be insignificant compared to the existing concentration. But compared to 0, no number is going to be insignificant. So we do have to include the 2S here, and then that'll be squared. And remember, the squared applies to the 2 and the S. And from there, actually, I'm going to try and do it on here. I think this calculator just kind of does this automatically. No. Still some getting used to the new iOS. There you go. Okay, cool. Oh, right. So to solve this, we're going to do 1.46 e to the negative 10 divided by 0.25. This is 5.84 times 10 to the negative 10. And I'm going to multiply this out. 4s squared. So divide by 4. And then the square root. 1.21 times 10 to the negative 5 equals S. I don't know if we're going to get to it today. There's one problem. Actually, I think this should be molar. So 1.21 times 10 to the negative 5 molar would be the molar solubility. Especially with these problems where we're calculating really, really small numbers, depending on your calculator, you might want to put it into scientific mode, where it'll give you all of the numbers in scientific notation. There's at least one example problem where, because it's like 10 to the minus 8 or 9, the calculator only displays 9 digits. And so you only get one significant figure because it lists all of these zeros first and then 7. But there are decimals after that, and it doesn't show you. Wait, we calculated this before, right? So if we look at the molar solubility here, this is 1.21 times 10 to the negative 5. And since we're talking about the effect of a common ion and how this suppresses the solubility, we can look at the molar solubility up here where it's 3.32 times 10 to the minus 4. So previously, actually, I'm not going to circle that because it's not an answer. So by having ions already present, we've decreased that molar solubility by a factor of almost 10. Every time I say previously, I think previously on Lost. Except Lost is now getting to be like really old. All right, so common ion effect. Which of these? No. Oh, wait, I should, no. Which solution of barium sulfate is most soluble? Or we might say has the highest molar solubility. Yeah. So remember, if I already have any ions that are in solution, that's going to make my molar solubility less because, the equation here, SO4, would give me barium 2 plus and sulfate, which is SO4 2 minus. So this is an equilibrium. So anything that gets added to the right side of this equilibrium, Le Chatelier's principle says, will shift this equilibrium to the left. So here I've got barium. That would increase the barium concentration, which would reduce my molar solubility. Sulfate, also on the right side here, would also decrease my molar solubility. But sodium and nitrate have no effect on this equilibrium because they don't have anything that's a common ion. So of course, we got to talk about other important ions in solution, and pH is one of those. H3O plus or OH minus concentration. And actually the lab this week kind of play around with this in terms of influencing these complex ions with different concentrations of different things. Sometimes it's hydroxide, and so if you add something like ammonium hydroxide or an ammonia solution, right, ammonia plus water makes NH4OH, and that hydroxide ion can react with things. So if I have something in my solubility equation, like the chemical equation that defines the solubility or the ions that are produced in solution when something dissolves, adding hydroxide here shifts this equilibrium to the left. If I do anything that removes hydroxide, then that'll shift this to the right and increase the solubility. There's another way that things can be affected less directly. Like obviously I can add any acid and decrease the amount of hydroxide present, or I could add any base, sodium hydroxide, potassium hydroxide. If I just add directly hydroxides, that increases this. But now that we've covered most of acids and bases, we also have things like weak acids and weak bases, and more specifically from, I think it was actually chapter 17. Yeah, chapter 17 was acids and bases. The conjugate bases of weak acids can also be affected by pH. Oh wait, I thought that was the next. Oh yeah. Yeah. So in general, the solubility of an ionic compound with a strongly basic or weakly basic anion increases with increasing acidity. So as you increase the amount of acid present, strongly basic, that makes sense. It's got hydroxides in it. Adding acid is going to neutralize hydroxide, is going to make things dissolve. Weakly basic anions, though, things like sulfide and carbonate. Right? Carbonate is the conjugate base of carbonic acid, H2CO3, which is not one of the 6 strong acids, which means it's a weak acid. So the conjugate of that weak acid is going to be a weak base. And it's actually calcium carbonate is limestone. And things have gotten a lot better in terms of acid rain. But like when acid rain was a big deal, there was a potential in areas that have a lot of limestone underground. The more acidic the rainwater gets, the more that dissolves, the more that you get sinkholes. Because the surface isn't limestone, but down underneath it is. That dissolves, that trickles away, creates large voids underground that weren't there before. Not to add another fear or unlock a new fear for anybody. We don't really have that problem around here. But even with just the natural acidity of CO2 dissolving in air to make carbonic acid, that can cause caverns to form. So again, we got to think back to chapter 17 to answer this question. So which compound, iron carbonate or lead bromide, iron 2 carbonate, lead 3 bromide, is more soluble in acid than base? So we got to take a look at these ions. So iron 2 plus, CO3 2 minus, lead, lead, that was a terrible 3 plus, and Br minus. We have to think about, are any of these conjugates of weak acids or weak bases? Carbonate, which is the one we just talked about. Yeah. Yeah. And again, the way that I always do this is I think if I look at the anion, I add hydrogens to it. So if I look at carbonate and I add hydrogens to it, that'll give me H2CO3. And then I say, is that a strong acid? Which the acronym that I like is BICPENS, which is, these are the so hydrobromic, hydroiodic, and hydrochloric acids. And then perchloric, nitric, and sulfuric acids. So carbonic acid, H2CO3, not on that list. Which means, actually, what does that mean? If carbonic acid is not on the list of strong acids,
increases in an acidic solution.
yeah, that's a couple jumps ahead of what I was thinking, but yeah. So yeah, no, I was just going back to, this is a weak acid. So what does that make CO3 2 minus? A weak base. Which means that the concentration of CO3 2 minus will be affected significantly by acid in solution. So if I add acid, it'll react with the carbonate to turn into carbonic acid, which means that I remove it from that side of the equilibrium, which means that I increase the solubility of iron 2 carbonate. Now for lead bromide, again, do the same thing, add hydrogen to bromine. Is HBr a strong acid? Yeah. Which means that bromide is not a strong base, it's not even a base at all. Neutral. Yeah. And that one, I know you think like, oh, if it's a weak acid, then it's a weak base. If it's a strong acid, it must be a strong base. But it's not the case, because weak acids are weak bases because they actually like to hold onto their protons, which means that they don't give them up very readily, which means that they will accept them pretty readily. But strong acids are strong because they completely get rid of their protons and they do not take any of them back. And for something to be a base, at least by the Bronsted-Lowry definition, it has to be a proton acceptor or a hydrogen acceptor. Bromide's not going to do any of that. Wants nothing to do with its little hydrogen. Poor little hydrogen. It'll get adopted by some weak base. So that means that this lead-3 bromide, not affected by acid. So iron carbonate is going to be more soluble in acid. So there's kind of a whole ladder of things to consider. Small things. Take a while when you say them all out loud. And again, kind of an extension of the common ion effect.
Would that mean that lead bromide is more soluble in a base?
Possibly. That's a good question. Yeah. Question was, is lead bromide going to be more soluble in a base? It won't be affected by acid or base. The iron carbonate will be affected. It'll be less soluble in a base. To know if lead bromide is less soluble, to know if iron carbonate is less soluble than lead bromate, we'd have to actually compare their molar solubilities, which I think actually perfectly goes into this next section, which is like, how would we do that? How would we even calculate if something is more or less soluble, or at what point do they dissolve or precipitate in different solutions? So this is quantitative, meaning we're determining the quantities of things that dissolve and the concentrations at which they dissolve, which is different than qualitative analysis. So again, we can draw on all of the things that we know about equilibrium in order to figure out if something's going to dissolve at a certain concentration. And we're using the same concept of K and Q, where KSP is the value of the product at equilibrium. Q would be the value, so this is at equilibrium. Q is the value of the product under any conditions, which does include equilibrium. So if you calculate Q and Q is the same as K, then it's at equilibrium. But Q is just like, in general, could be anything. And I used this example, and it's been helpful for some people. If we think of K and Q as a sort of number line, where this is product heavy, this is reactant heavy, and in the middle is 1, so exactly balanced. We can place KSP on this number line. And actually for a lot of these, we're going to be really, really, really close to all reactants, right? Because generally talking about things here that aren't very soluble, so that means that their K values are really, really small, which means that they're going to be really close to the reactant side. But as an example, let's say that KSP is here, somewhere between 1 and being reactant heavy. When I calculate Q, I can place it on this number line as being either larger or smaller than KSP. And a lot of the time in this chapter, we should really be focusing on just this side where everything's smaller. So if I have a Q, if I calculate Q and Q is here, which way does that reaction need to move to get to KSP? To the left. Which means that I've got more products than I have reactants at equilibrium. And so this will go to the left. And if I start to the left of KSP, then it's the opposite, right? I have more reactants than I should have at equilibrium, and this will move towards KSP. Now for solids, if Q is greater than KSP, then the solution's supersaturated, right? Because the amount that dissolves at KSP should be the maximum amount. So if I put in anything more than that, that will give me a supersaturated solution, and solid will normally precipitate out of the solution instantly. If you add anything more, it'll precipitate out. You can get situations where it is supersaturated. I should have brought them. I have some hand warmers that have sodium acetate, or I think it's a sodium acetate solution, and it's supersaturated. And if you give it a shock, it will all precipitate at the same time and generates a bunch of heat. So that would be a supersaturated solution that you can kind of control. And then by heating it up, you can get it to dissolve again. And this is a little bit of a tangent, but why is that even possible? Okay, yeah, I should rephrase my question. How can I have a supersaturated solution and heat it up and make it redissolve again? Because if I'm heating it up and it dissolves, that must mean that KSP is changing. We don't talk about it that much in this class. Well, actually, we'll talk about it more later when we start talking about thermodynamics. But KSP is for a certain temperature. A lot of the times, like we've treated it as just like, yeah, it's a constant, like it has to be at the same temperature. But for sodium acetate, that KSP must move enough, at least, that I can get it to heat up. That KSP moves to the right. Everything dissolves. And then as it cools down, the KSP moves back to the left. But without a site to form crystals on, the sodium acetate stays supersaturated. It's also kind of cool because you can think of it as a thermal battery. The fact that you have to heat it up again to make it redissolve. It then stores all of that heat until later. And then you can activate it and it releases all the heat that you stored by boiling it. Okay, back to precipitation though. So above KSP, solution is supersaturated. Below, it's unsaturated, meaning you could dissolve more, or you wouldn't expect to see any of it precipitated. If Q and K are the same, then you're at the saturation state. You have as much dissolved as possible, which also kind of aligns with why we leave solids out of this equilibrium. When this is at equilibrium, the concentration of the solid is constant. And since it's constant, we don't include it in this equation. So sort of the practical math of this is that you can use Q to predict whether a precipitation reaction will occur when two solutions are mixed beyond just memorizing solubility rules. Because like we said earlier this week, solubility is more of a spectrum than it is like yes or no, it does or doesn't dissolve. Everything dissolves a little bit. Some things just don't dissolve very much at all. So what we want to do is we want to calculate Q, compare Q to K, and see if my Q is larger than K, and then how much will precipitate. So if you have a solution containing lead nitrate mixed with one containing sodium bromide to form a solution that is 0.06 molar in lead nitrate, 0.0158 molar in sodium bromide, does a precipitate form in the newly mixed solution? So really what we're concerned with here and what we want to know is, does a precipitate form? They do give us the KSP for lead bromide. So that's probably what we should be looking at. If it's not given, then you've got to sort of swap your ions, do a double displacement reaction, figure out if either of those two things is going to be soluble, and then look it up in a table of KSPs. But here we can just focus on the lead bromide. So lead bromide, we're going to write out a reaction for the KSP. Now we need to figure out how much. Oh, and actually, I want to point out here, earlier when I said, like calculating molar solubility, we have a solid, some of it's dissolving, molar solubility tells me how much. So there's like an initial, there's a change, there's an end. My initials would be 0, my change would be how much more becomes, or how much becomes those ions in solution. And then I would have an end state. But here, we're not doing that. We want to calculate Q. And Q for this reaction is going to be the concentration of Pb2 plus and the concentration of Br minus squared. So this is not an ice table. So what's my initial concentration of lead going to be? 0.06 molar. All right, so if we look at this lead nitrate, there's only one lead in there. You do have to be a little bit careful here that, if there's like two, there's going to be twice as much nitrate in the solution than lead. But I don't care about nitrate for this problem. This is going to be 0.06 molar. And then how much bromide do I have? Yeah, 0.0158 molar. And really, I just need to plug those concentrations in and calculate Q. me do this. Yeah. 0.06 times 0.0158 squared. So my Q is 1.4978. I don't really need all those, but times 10 to the negative 5. And now I need to compare that to my KSP. So that's 4.67 times 10 to the negative 10 to the negative 6. Kind of wish the decimal part of this had been higher, but that's okay. So is Q larger or smaller than K? Yeah. And actually, I honestly was thinking of that a little bit backwards. So yeah, 10 to the minus 5 is bigger than 10 to the minus 6. Honestly, the better thing that you can do here is try and get these into the same scientific notation. So if I take 1 1.4, stop switching. Okay. 4.67 times 10 to the negative 6, I can make that into 4.67 times 10 to the minus 5. If I move the decimal one place to the right or to the left. So instead of, I keep accidentally switching to the eraser. Oh no, I keep switching to the, got it, all right. So 0.467 times 10 to the minus 5. And now that they're both in the same scientific notation exponent, I can just look at them directly, and it's obvious that the Q is larger than K. And we could apply this number line idea, reactants, products, 1. And again, these are all really, really tiny numbers. So KSP is here, Q is larger. So if that's Q, this is K. That means I need to go to the left. And my reactants in this case, or my reactant, is the precipitate or the solid. So does a precipitate form in the newly mixed solution? Yeah. Q is greater than K, which means I have more ions in solution than I should at equilibrium. Any questions? Oh, I have added office hours on Fridays now from 11 to 12. So if you have other questions, to sort of tee up what we're going to talk about next week on Monday, is really starting into selective precipitation. Selective precipitation honestly covers also qualitative analysis. Qualitative analysis is I add one thing, or I add things like hydroxide, ammonia, chloride. You add different ions, anions to your solution and try to figure out which cations are precipitated by those anions. And we'll talk about that whole flow chart later. The first thing that we're going to talk about here, though, is how concentration can actually be used to selectively precipitate two different things. So one of the first examples that we'll look at is actually between calcium and magnesium. And these have very different KSPs for their hydroxides. So KSP of magnesium hydroxide is 10 to the minus 13, much, much smaller than calcium hydroxide, which is 10 to the negative 6, which means that if I'm really careful with the amount of hydroxide that I add, I can actually precipitate all of my magnesium without really touching the calcium concentration. And so you could do things, I mean, there's a lot of stuff you could do with this, but one of the things you could do is if you want to collect magnesium, let's say out of some wastewater stream from a factory or something, because you could resell that magnesium as magnesium sulfate, which are Epsom salts. You can take this, add just the right amount of hydroxide, filter out all of the magnesium, and send the rest of the waste solution along its merry way. And then maybe later you add more hydroxide to precipitate out all of the calcium separately. But we'll do the math for that on Monday. Qualitative analysis, which we'll also hopefully get to on Monday, talks about the process of just like adding things to solutions, precipitating things one at a time, because they don't both precipitate with hydroxide. And before you leave, I've left some time for the dean to talk about evaluations and the questionnaire.